I'm really looking forward to this one. So I hope you still have some energy left to listen for the last one. Because yeah, this is a lot about also trying to explain how we use the mathematics to produce new results and solve new problems. And so. The magician. Thank you. Yeah, always we come back to this. So where are we now? Well, this is really the core analysis part of the cornerstones of the Ram-C and LCM. So it's on the optimization part here in the analysis corner. So that's where we are. Okay, so I'm going to start with a statement. I think that you should use OPUS Evo, which is a new software in the OPUS suite. You should use it for deployment or any short-term tactical optimization. If you want to improve the expected mission capability, or spend less money, or lower the risk of failing a mission, or all of them at the same time. Okay. So to explain how this all works, I'll start with like a little teaser. We did a real-world use case. It was the F-35s for the US Air Force. They were going on a short notice deployment. They were going away for 20 days. They were planning for this mission, I should say. They were planning for this mission. They were deploying 4 fighter aircraft, these F-35s, to a foreign country, and they had limited resupply support during this period, and they wanted to find a good deployment spare package for this operation. Okay, so we helped them with OPUS Evo, and we could prove a 50% increase in mission capability for this deployment with the spare package that Evo could calculate. We could also reduce the number of spare parts with 38%. And for deployments, that's good because it means less volume, less weight for the transport. And also, we could reduce the cost with 56%. So this is the US Air Force deployment spare package model. So they had an internal way of calculating this, which produced a result, or the spare package that this tool recommended, were costing them $33 million. And the solution that OPUS Evo produced was only $14.5 million. So that's a real world use case that we did, just to show you the power of this as a start. But how is this all possible? How does it work? Well, then let's move to the beginning again and talk about evolutionary algorithms, which is the approach that we use with OPUS Evo and that makes this type of optimization possible. The approach in general is it's a general and it's a robust approach for optimization. It's an evolution-based iterative approach. I will explain more what I mean soon. But anyway, it's not something that we at Sytecon has invented, but it's a mathematical method that is used in a range of different applications, such as in the medical treatment, for example, for cancer treatment, also in different scheduling, application scheduling problems, and other logistic scenarios as well, apart from ours. It is very friendly with more and more modern computers, and the ability to scale the functionality, the computational power scales very well with multiprocessors and multi-cores and multiple computers simply. So we can solve larger and larger problems if we have more computers and more computer power. And it is sort of a black box optimization. It means that it's unrestricted by any mathematical constraint, so we don't need any we don't need an analytical, like a formula, how we calculate this. It's we just can optimize any parameter given any with any objective functions. And you can say that like this: if you can model something, then you can hopefully evaluate it. So it means that if we have a model, you know, we talked about data and data model and so on, and if we have a model and we can evaluate the outcome of the input data in that model, then if we can evaluate, we can also optimize it with this approach. So how does it work? If we look over on the side there, so it's really mimicking the evolution. That's why it's called the evolutionary algorithm. So we start with some kind of random samples. So randomly select a way of doing things. And then we evaluate those samples and we select the best ones of them. So that's what we mean with evaluation. So if we can evaluate it, then we can also define which of the samples that is better. So that's a core here. We need to be able to measure the different alternatives between each other, differentiate them. Okay, so we call those the parents. And then we combine those parents, sort of like we do in real work, we're combining people, and then we create new ones. So we get some offsprings, we get new samples. Again, we can evaluate them towards each other, and we sort of say the ones that are most successful, and yeah, that's what's often referred to as the survival of the fittest. So let's take a pretty interesting example. This is a picture from the Swedish coastline, the archipelago. So this is how it looks. And if we want to defend our coastline, we need the Marines out there. So here's a guy that's going to defend Sweden. And we want to create a camouflage. He needs to be able to hide out in the islands there. This camouflage that he's wearing right now is not so good in summertime. Actually, in wintertime, it would be perfect in Sweden because it's snow and ice everywhere, so he can hide in winter. But in summer, it's not so efficient. So if we use this as an example on the algorithm, we start with a set of random samples, a set of randomly created variations of this camouflage. And then we evaluate them towards each other. So this is the important part. We need to be able to tell which one is better. So if we can rank them and say that the guy in the middle there, the blue one, it's the best, it's number one. And then we have number 2 and 3 and so on. So if we have this, we can now combine different outcomes here to create new ones. So the first one would probably be to combine number 1 and 2. And that camouflage will look something like this. And then we combine 1 and 3 and create something new. 1 and 4 and get another one, and 2 and 4, etc. And after a while, we have a set of new samples here. And then we replace the weak ones with new ones. Of course, we start again from the start. We evaluate those, and then we combine them, and we create new ones, and so it goes on for as long as we wish. If we want to continue, are we happy now? Maybe, maybe not, and then we continue another iteration until we have a satisfactory result. And in this case, this was the final camouflage that we are satisfied he can hide and protect our country. So that's how that's really how it works. But I mean, with OPUS we use our simulation tool Simlogs to be able to produce those. To be able to compare the different samples to see which one is better. So that's why Evo fits very nicely in this picture, because we have a model here, right? We have the Opus Suite model that I talked about before as well. We have and hopefully we have gathered the information here, we got it in, we have built our model, and then we can use, what we do is that we use Simlogs as an evaluator to tell if one song is better or worse than the other. So this is what Evo does. It's a very good complement to the rest of the tool suite. Yeah. But it also, because it incorporates the dynamic aspects, come back to what I mean with that in a bit. Here's an example on another example on how an evolutionary algorithm can work, how it searches. It doesn't get stuck. I mean, this is a complex mathematical picture, but it typically shows you a lot of local minimums. You want to minimize this function, you want to get as low as possible on the surface. But and with analytical approaches, it's very hard to find a solution to such a problem because there are so many local minimums. But with an evolutionary approach, we don't get stuck, but we can continue finding that global optimum as well. And I mean, this takes a lot of computer power because we need to run the evaluation many times. We need many samples, and we need to do it many times. But this approach scales very well, as I said before, with computing power. So the bigger the problem, you might need more power. You won't need this much, but just for showing that the more computer power we have, the more complex problems we can solve as well. And I mean, as of today, it's kind of computer power is comparably to those defense systems that we're looking at. Computer power is pretty cheap. You can get up like 60 computers on an Azure cloud for not that many dollars. So compared to what those, if you recall the numbers from that F-35 example, I think we were talking of tens of millions of dollars. So computer power is cheap compared to spare parts for fighter aircrafts. Yeah, scaling. So if we just go through the differences here between, because I think it's good to understand the differences and the pros and the cons with the different tools in the Opus suite. So Opus 10, it's our classical cost-effectiveness optimization tool. It has the analytical approach, so sort of calculating using formulas. It's exact, which makes it extremely fast and can handle almost any problem size in a matter of minutes. And it gives you optimized spare suggestions. Simlogs is the simulation. We are not locked to a steady state. We can build any dynamic scenario with variations over time. We can also evaluate the present results for a certain set of input parameters. This means that if you want to try something else, try a different alternative, you need to manually update your input data and then see if that was an improvement or not. So that's what Simlogs does. It's an evaluation of one suggestion. And with Opus Evo, we can optimize those dynamic scenarios, which produces new suggestions following a certain set of input boundaries. And it uses Simlogs to evaluate each such suggestion. And this is an automatic approach to find optimal solutions. This is just another way of comparing Opus 10 to Simlogs. So Opus 10 is typically long-term and Simlogs typically short-term. We talk about strategic optimization and tactical simulations. Not necessarily. I mean, we can model long-term solutions with simulation as well, and we can do strategic simulations as well. But the next one is important. Opus 10 is a steady state model, meaning that we are only working with average rates and average values. So there's no time variations in such a model. However, with the simulation, we can handle any time dependencies. So variations over time, different, for example, changes in failure rate over time or changes in repair times, etc. With OPUS 10, we have fixed objectives. We are always minimizing the cost per number of back order. So that's fixed. Simlogs, well, yeah, it's not really, there are no objectives, to be honest. It's more like we run the simulation and then we have a lot of different results to look at. With OPUS 10, we optimize spares. With Simlogs, we can look at and evaluate spares, systems, and resources, and many other things. And so on. But what's important here is that it's an analytical optimization, while Simlogs does only evaluate one suggestion at a time. And that's a manual approach. So if you want to evaluate many different alternatives, that's going to take you a lot of time to do manually. But here comes OPUS Evo, which is able to handle any of the variations from Simlogs and perform automatic optimization of those solutions. And we can also actually select any parameter in Simlogs to optimize. We can select which, if it's an input parameter to Simlogs, then we can optimize that parameter with this approach. Okay, so how it looks. Input into OPUS Evo is just a standard Simlogs model. And then you give some, here in this example, it could be others, but for now we look at, we want to optimize the number of systems for this deployment. We want to optimize the spare parts and the maintenance resources. So we give, we need lower and upper bounds to set the boundaries of this, because otherwise it would be infinite. So we'd say that the number of systems is between 0 and 100, that's fine, but it cannot be infinite. Okay, and same for the others. And then what we get out is that we get, out of Evo, we get an optimized number of those parameters that we put in as optimization variables, the systems, items, and resources. And we get them as input tables that we can feed back into Simlogs and keep on analyzing the answer. Okay, so that's the background. I hope it was somewhat clear. And now I want to go into a more detailed scenario and a demonstration on how this works, which hopefully makes it even more clear how it works. Unfortunately, we cannot use the F-35 example here because kind of sensitive data and stuff like that. So we, as a demonstration scenario, it's similar, but it's fictive. This for the demonstration purpose. But it's the exact same method as was used for the F-35 case. So anyway, here we're looking at some kind of land vehicles. It's armored land vehicles. We have 3 different types of these battle tanks in the example. They come in 3 different configurations. And they consist of 100 100 parts or items. Of course, each item has a failure rate expressed in different operation parameters, which you can do with OPUS Suite. So we can say that the failure rate can be measured in operating hours, but it can also be measured in the number of terrain kilometers that is driven. So this is sort of similar to what Oscar talked about before, that okay, we can actually handle different operation environments and say that if we're going terrain kilometers, we have more failures maybe, or road kilometers, or firings, or rounds with the weapon system, and so on. Okay, we also know for those 100 items the price, the weight, and the volume. And as we are talking about, always talk about, someone asked about AI and so on. So in this case, we actually used ChatGPT to help us create the weight and the volume for those 100 items, because we didn't have that information, and it actually gave us a pretty, I think it's hard to read, but gave us a really good outcome here, so that we can input directly to Simlogs. Of course, it's for demonstration purposes, but it was kind of a fun exercise to use it for that. So, okay. So for the scenario, we have 2 different sites. We have, this is in some country, an imaginary country. We have a north location where we're going to deploy those vehicles, and we have a south location where we want to deploy. And they're going on a mission for 90 days. So it's a 90-day endurance period, which means that we cannot send in any new spare parts. The stuff that we go there with is what we have. We cannot add any additional spares, and we can't repair them either. Anyway, here's an operational profile for each of them, which is important to notice is that they are different for the north and the south location. I don't think you can read those numbers, I can't either, but what it says is that the total operating system hours is it's the north one, which is higher, so it's 3,500 operating hours in total for all the battle tanks that we sent there, when it's only 1,500 at the south location. And as you see, this is not steady state. This is a time-dependent operation profile. So we're going on missions, then we're back on mission, and like that. And it's only 90 days, so that's also important that it's sort of a short period, which makes it hard to use the steady state assumption, because steady states are not time dependent. So here we're looking at a short period, so that's why it's important. Okay, and then there is some kind of military control center here that are asking questions. And so the assignment for the OPUS analytic team is to find a spares package that maximizes the achievement of the planned operation time. So when we play this as a little game here, so we say that first day, the military command team here, they are asking, let's say that we are the OPUS Suite analytics team here. So they ask us to provide a spares package that maximizes the achievement of planned operations. The maximum budget is $5 million, and the maximum weight that we can bring on this mission is 20 tons. Okay, sure. We will get back to you soon with an answer. So we go back, we model this in Simlogs. We build up our Simlogs model with all the information. We have the north and the south locations. We have 15 armored vehicles at each, 5 of each different configuration, etc. And then we have Evo at the other hand, and we run Evo as I said, repetitively with the evolutionary algorithm. So what happens? This is the outcome of one run with Evo. You see over time here, what we're doing is that we are iterating according to the evolutionary process. So we are, for each iteration, we increase the mission success upward as we go. So here we're doing 100 iterations. So as you see, the mission success is increasing for each iteration in this evolutionary algorithm. And finally, we end up here. What I was first going to say that here we see on those other two graphs, we see the number of items. Here is 100 items on the x-axis at the north stock, and down here, the same 100 items at the south stock. And as you saw, it was changing over those 100 iterations because we are testing different values on the number of items. And then we evaluate them, see what is the outcome. If it's good, we keep it. If it's not good, we don't keep it. And then we continue like that. And here we did 100 iteration, and then we say that, okay, it's sort of flattening out up here. So we're kind of satisfied with the result there as well. But if we look at this stock graphs here, we see that there is one item that's really sticking out much more than the others, and it turns out that this is it's called the pad steels. So the steel pads on the tracks of this vehicle. There are many of them, so we need many. They often break, and we need a lot of them as spare parts. Okay. And if we look at this again, and if you remember, we had constraints as well. So in the middle here now, you see the constraints that we had on this for this analysis. Sorry. So we had two constraints. One was $5 million. We cannot buy spares for more than $5 million, and the other one is that it is not allowed to weigh more than 20 tons. And this is kind of interesting because what you see here is that it was obvious that it is the weight that is the limitation, not the cost. We could have bought more in terms of cost, but not in terms of weight. And that's a good conclusion. Why? Well, because if we're not happy with the result that we got here, with the mission success rate that we could reach, then we can come back and say, well, hey, yeah, we have money left, but we don't have any weight we don't have any more weight. So maybe we can transport in another way, or more money into that, and we can increase the mission success as well. So anyway, we ended up here with 96.6% success rate. Okay. Second day, we have a discussion with the team here, and they say that, oh wait, you are suggesting too much spares because we can only take the ones that we have in stock. We can't buy any new spares, we can only take the ones that we already have. So that means that the ones at the bottom here that are marked with yellow, they are exceeding the red lines. So for example, the pad steels here, you see the red line is the number of spares that we have in-house, and the blue bar was the optimized amount. So we have another restriction. They ask us to make a new calculation which takes into consideration the number of existing stock. Okay, let's do that. So we add another restriction, the red bars here, saying that there's a maximum value on the number of spares that we can deploy for each type of spare part. And we run it with OPUSU again. You see how we have the red lines at the bottom graph here showing the maximum values on for each of the spares. And now you see that after 100 iterations again, it flattens out here, the mission success. And we also see that all the blue bars are now behind the red lines, meaning that we are compliant with the constraint on the number of spares. And in the middle, we still see that the total cost is only half the budget, while we are maxing out the weights. So now, obviously, we increase the success rate that we are able to achieve. We went from 96% to... thanks. Of course, we decreased, not increased. We decreased the mission success from the 96% that we had before to 86% now. And that's, of course, because we put on another constraint saying that we cannot send any more items. So, next day. What happens now? Well, they come back and they say, well, thanks for that, but there's a problem. The container volumes we have constraints that are different for the two different units. We have the north and the south, as you remember. And we say, okay, before we said that there was a weight constraint, but there might be a volume constraint as well. There's a volume saying that we can only send 10 cubic meters to the north unit and 5 cubic meters to the south unit. So that's another constraint on this. Sure, let's do that. So we add this to the EVO calculation, to the input as another boundary that we're not allowed to exceed. And now it's in the middle there. You see them here. Oh, sorry, it started again. But anyway, those you see the north unit here and the south unit here, and with our constraints of 10 cubic and 5 cubic meters. And you see now that those are the ones that hits the roof, so to speak, which means that they are the constraint now. They limit us in what we can achieve. And once again, the mission success has decreased. We had 86 before, now we're down at 79. So with another constraint, yeah, we have to accept that we decrease the mission success because this limits the number of spares that we can bring. And the maximum output here is 79%. Next day, I'm assuming this is the last day. Anyway, now, they say, thank you, that was nice, but this is not good. We need better performance of the systems, right? We are not happy with 78%. We need more. So we have a suggestion, and it's that you use something that we often call robbing, or maybe also known as cannibalization. If we have one system that is stopped due to maintenance, then we are allowed to take parts from that one and put it on another vehicle. Okay, so that's a sort of an emergency measurement that you might take in certain situations. But we can actually model this with Simlox, which means that we can optimize it with Evo. So that's fine. We add this to the Simlox model, and this is very small font, so it's impossible to read, I understand that. But what we do in Simlox is that we say we enable robbing in the control parameter here. Okay, yes, it's enabled. Fine. And then over on the far right there, we add robbing replacement tasks. Just saying that, okay, if this vehicle is stopped, we can actually take out something from it to put it on another one that's functioning. Okay, so we sort of temporarily borrow something from one system to be able to use it for another one. And then we run Evo again. What happens? Well, we have our constraints in the middle, and we have the stock total at the bottom, and we are looking at the mission success rate at the top. It is still the volume constraints here that are limiting us because they are up in the roof. So as you see here, but anyway, what happened now was that we're back at 88% because we allowed this robbing approach. And it's kind of interesting because you see here, you remember the steel pads that we had like 100 of before, now we have almost none. And that's because as soon each vehicle here in this model has, I think it's 180 or something steel pads, each of them, which means that when one of them is stopped and we don't have a spare part for it, then we have 180 to take from that one. So that means that we can run the other vehicles instead. And again, improving the mission success considerably. Thank you, they say. They're happy with us. You're welcome, so that's great. Perfect. So conclusions from this is that in this scenario, we could show how OPUS Evo was used to efficiently find out spare packages that satisfies not only cost effectiveness, but also a series of other constraints, not just the cost, but also the weight and the volumes. But now this was, as you saw, we were only actually tweaking the items. We were only talking about the items, but we could do the same thing for the number of systems or the number of maintenance resources as well. So it's actually, yeah, it can become more complex or wider as well, but for demonstration purposes, I think it was good to keep in one dimension, so to speak. So we looked at the items. Yep. So yeah, I think it's fair to say that OPUS Evo is powerful and it can solve real-world problems, and it uses this horizontal scaling of computer power. And that concludes the introduction of OPUS Evo. I hope that you found it interesting and that you can take something with you here regarding evolutionary algorithms and how they can be applied in logistics scenarios. Do we have any questions?
I just wanted to clarify one thing with the picture with all those computers. That was an illustration. I think it's all dependent on how big the problem case is. So this example here was using a regular a pretty good standard PC to calculate it. But when you add more parts and more degrees of freedom, of course, then you will add more complexity, and then you will need more computational power. Yeah. So you don't need to have a computer lab just to use it.
No.
혹시 뭐 아무 질문이나 하실 분 혹시 계시면?
대표님, 아까 마지막 시뮬레이션 타입제 때 시뮬레이션 왜 했는지 그 부분이 좀 잘 못 들었는데요.
여기서요?
네, 아까 첫
대입
번째까지는 이 용량, 컨테이너 용량 그거를 얘기하셨던 것 같고 그 마지막에 거는
마지막에 대입인가요?
네,
예, 대입.
그거는 뭐 때문에 다시 한 건지.
Okay, could you explain from the beginning, day 1, 2, 3, 4, why simulate model could be changed? What constraint, what type of model is changing? Something. Yeah.
Yep. Okay. So what changed was I can use this one. So what changed was these constraints that we were talking about. So from the beginning, we said that we only had a limit on the total budget, right? It was $5 million, or I think it was $5 million. And we had also a constraint on the total weight in kilograms or in tons. And then for next day, we added a restriction on the volume, exactly. There's one more. I'm missing one. Sorry.
I think it was the total volume, and then it was.
So first one was budget and in money, in investment, in spares, and then it was maximum weight. Yeah. Okay. So it was actually no. The first one was that we were proposing more spares than we owned. So, for example, we are owning 10 spares, but we suggested to bring 12. But we only have 10, so we cannot bring 12. And there is no time to buy 2 more, or there's no budget for that. So the first constraint was actually to limit the number for each part to the number that we own today. So that was number 1. And then number 2 was the volume constraint. Had it? That was exactly, that was the first one, and here's the second one. Yeah. So we said that we add also a constraint on the volume of the package. So we need to know how big is each spare part in its box. So that was the second constraint. And then it went really bad. So then we added this. Oh, I'm not showing that. It doesn't matter. Then the last thing was to improve, to make it better again. We introduced this robbing or cannibalization, that we steal from others. Yeah. So that was not a constraint. That was a way of making it better again, so to speak. Okay. Perfect.
우리 국방에서 훈련 되게 많이 하죠. 미션의 일종으로 훈련을 되게 많이 하는데 훈련을 미국하고도 많이 하고 우리 독자적으로도 많이 하는데 거기에 미션 석세스 레이트가 혹시 계산되는 거 봤어요? 그런 훈련에서 형편없이 낮을 거예요. 제가 알기로. 또 우리가 주로 그 미국하고 연합 훈련을 할 때 수많은 무기 체계가 동원이 됩니다. 그 수많은 무기 체계가 동원이 됐을 때 비용이 어느 정도 들어가지고 어느 정도 미션 석세스를 가졌는지 이건 훈련이니까 상관없어요. 만약에 근데 이게 전쟁이라고 한번 생각을 해볼게요. 우리 무기 체계의 정보를 가지고 시뮬레이션을 해봤을 때 군수 측면에서 우리가 전쟁을 석세스풀하게 수행할 수 있을까? 이건 한번 생각을 해보셔야 됩니다. 두 번째, 우리 해군의 무기 체계 같은 경우 한번 보세요. 우리 군수 지원이라는 개념이 도달이 안 됩니다. 왜? 배 타고 나가야 되죠. 이랬을 때 우리가 군수 지원을 어떻게 해야 되는지 이런 거에 대해서 분석을 한 적이 있나요? 안 합니다, 우리나라. 모든 기준은 육군 기준이에요. 이러다 보니까 이런 식의 개념이 전혀 없고 이런 식의 그 다음에 이게 선험적인 거예요. 우리가 미션을 안 해봤는데 어떻게 분석을 해? 이런 개념이란 말이에요, 우리 입장에서. 산업적인 개념은 우리가 경험적으로 해결을 해야 되는데, 뭐다? 시뮬레이션 밖에 없어. 그래서 시뮬레이션 기법 플러스 옵티마이제이션 기법을 적용을 해서 매 단계별로 상황이 바뀔 때마다 어떻게 시뮬레이션을 해서 우리가 비용이나 기타 군수 지원 요소들을 추출할 수 있는가, 이게 상당히 중요한 문제인데 불행하게도 아직 거기까지는 안 가 있습니다, 우리나라는. 그래서 여기 계신 분들이 그런 것들을 이렇게 할 수 있도록 하셔야 될 것 같아요. 이거 저 계산하는 것 때문에 지금 슬라이드를 이렇게 간단히 만들었는데, 계산하는 거 보면 상당히 재밌어요. 이렇게 움직이니까 재밌기도 하고. 그 다음에 아까 컴퓨팅 파워도 마지막에 얘기했는데, 뭐 어마어마한 머신이 필요한 건 아닙니다. 이 정도는. 지금 현재 수준의 컴퓨팅 파워 가지고도 간단하게 모델링을 하고 시뮬레이션을 충분히 할 수 있다는 얘기죠. 마지막으로 덧붙이는 건, 우리는 항상 평시만을 생각합니다. 전시 평시 이렇게 생각을 하는데, 우리가 굳이 똑같은 건 아니지만 개념상으로 평시라는 개념이 얘네들이 얘기하는 스테디 스테이트 개념이고, 전시라는 건 시간에 따라서 상황이 변해가는 과정이거든요. 그래서 타임 디펜던트한 문제인데, 예, 슬라이드를 뭐 요약 설명하고 빨리 끝내겠습니다. 수학적으로 정확하게 모델링이 됩니다. 최적화하는 것들이. 단지 제한 조건은 뭐예요? 스테디 스테이트라는 겁니다. 이 문제만 일단 풀 수 있다는 얘기고, 우리가 목적으로 하는, 그러니까 최적화하고자 하는 오브젝티브는 항상 고정되어 있습니다. 예를 들어서 스페어 가스 산출 또는 가용도 최적화, 이런 식으로 고정된 오브젝티브가 있다는 개념이에요. 요거만 되는 겁니다. 지금 현재 우리 국방에서 하는 것들이. 근데 이걸 발전시켜야 된다는 이유는 이런 것들이죠. 상황이 계속 시간에 따라서 변해갔을 때 우리가 어떻게 최적화를 해야 되느냐. 이건 아직 안 하고 있습니다. 해본 적도 없고, 우리 국방에서. 그래서 이걸 해결할 수 있는 방법은 아까 말씀드린 것처럼 시뮬레이션 기법으로 해결할 수 있는 방법이 있고, 지금 마커스가 설명한 OPUS 2부를 가지고 두 가지를 믹스를 해서 상황에 따라서 단계별로 최적화를 할 수 있는 방법들이 있는데, 우리 맨날 코스트는 무지하게 얘기 잘하는데 그 코스트를 분석하는 기법들에 대해서는 전혀 관심이 없다는 얘기죠. 그래서 이런 것들도 이제 좀 고려를 해야 된다는 얘기입니다. 그래서 아무튼 슬라이드 먼저 전달해드리지 못해가지고 죄송하고요. 이 슬라이드에 설명이 돼 있어요. 그래서 이 슬라이드를 이메일로 빨리 배포를 해서 참고하실 수 있도록 하겠습니다. 또 다른 질문 혹시 있으시면 예, 말씀하시죠.
교수님하고 상황은 다른데 세 가지만 생각하면 되는 줄 알았는데 오늘 교육을 받으니까 나머지 둘도 사야 될 것 같아요.
훌륭하십니다.
가격을 얘기하기는 좀 그렇고 기존에 스캔 기준으로 제가 거의 동일한 건 아니지만
동일하거나 조금 낮은 것도 있어요. 네. 저기 오퍼스 2번은 뭐 되게 툴이 좋아요. 문제는 좋은데 이런 백그라운드를 알고 이제 사용해야 된다는 문제가 있죠. 그냥 뭐 대충 데이터 넣고 담당하고 이런 개념은 아니고 자기가 글자 그대로 OMSMP 정도까지 만들 수 있을 수준이 돼야 돼요. 그래야지 상황을 집어넣고 시뮬레이션하고 단계별로 최적화를 하고 이런 과정을 거칠 수 있다는 얘기죠. 네, 어쨌든 잘 만들었다고 저는 생각을 하고 있고요. 그 다음에 아까 맨 처음 설명하신 그 인사이트도 비주얼라이제이션을 통해 가지고 빨리 어떤 의사결정을 할 수 있도록 결과들에 대해서 이런 것들도 잘 돼 있다고 생각합니다. 그 다음에 커넥트가 단순한 데이터베이스는 아닌가, 아까 간단하게 설명했지만 단순한 데이터베이스는 뭐 우리 델리스 쓰면 되죠. 자료 가져와 이렇게 하면 방대한 양의 빅데이터가 모아져 있을 때 여기서 어떻게 하면 우리가 제너러티브하게 데이터를 가져와서 빨리 분석을 할 수 있게 이런 인터페이스를 만들 수가 있겠느냐, 이런 문제를 지금 오늘 얘기를 한 겁니다. 혹시 또 다른 내일 혹시 교육 오시는 분 계세요? 교육은 이제 오퍼스 10부터 천천히 할 겁니다. 왜 그래서 이렇게 되고 이렇게 되고 이렇게 되고 이런 식으로